Okay, in the previous slides, we covered the motor control aspect of posture, and the last two slides will look at the neural anatomical relevance to the postural control. So in the beginning of 20th century, the scientists wanted to see whether the postural control is occurring in the brain, this forebrain, or in the spinal cord, or in the brainstem. So they started using the cats to look at the locus of postural balance control. And the easiest way to do this would be, so let's say this is the brain, brainstem, and spinal cord. Just cut through here and see what's happening to the behavior of these four-legged animals. So by cutting through this area, so the area between the brain, the forebrain, and the brainstem, is called decerebrate. The decerebration is the severing of all the information that's connecting to the big brain to the brainstem, or brainstem to the big brain, cerebrum. So when this was done, so especially the cut was between superior and inferior colliculus, as the midbrain area. What could be seen in this animal is called decerebral rigidity, which means even there's no input from the brain to control what to do with the limbs, the animal can stand unsupported. It was so rigid, all the extensors were fully activated, so the cat was able to stand without support. And the other thing observed from this preparation was the exaggerated reflex activities. You can also link that with the upper motor neuron disorder, which the input from the brain is removed, and as a result you'll see exaggerated reflex activities. Interesting thing is the cat was able to stand unsupported, but when the sensory nerves were cut, this preparation is done in dorsal root severance. So this is also known as deafferentation. Remove of afferent, which is sensory. So when all the information from the sensory the cutaneous sensation or proprioception and so forth was cut. So let's say this is the input towards the spinal cord, and this is will cut through the dorsal root severance. Then the cat showed collapse in posture, which meant sensory signal is crucial in maintaining this postural circuitry to be operating. So from this inferior and superior colliculus, what they did was the scientists moved the severing location slightly upwards. So more and more of the influence of the cerebrum would be shown in this preparation, and as a result automated response could be seen. For example, grooming behavior, yawning, or other more complex reflexes could be seen when that cut was going up towards the big brain. So you can recognize this pattern. The primary circuit for just the basic circuit would be embedded in the spinal cord, more complex towards the brainstem, and the most complex programs will be stored in the brain. What about humans? So we can't really do this experimental cerebration to humans, but what we can see is looking at the patients who had strokes in either brainstem area, other parts of the brainstem area. So decerebrate posturing is when they have the stroke in the brainstem area. For this case, is pontine stroke. So pons. So there's a pons, medulla, and midbrain. So the information is cut through at pons here. And this is the posturing of the decerebration occurred at pons. So you can see the limbs are all extended, similar to the decerebrate cats. So extension of the lower limbs, ankle as well, extension of the arm as well. Red nucleus is involved in upper arm flexion. And red nucleus can be found in the midbrain. So this indicates why the patient doesn't show the flexion of the arm, because the information from the red nucleus cannot go through the below pons, so it can't really affect the posture. So removal of the upper arm flexion shows the extension of the arm here. If the damage is higher up, so decorticate posturing might occur as a result. So decorticate damage to the area including 4 brain areas, so cerebral hemispheres, internal capsule, and thalamus. That's all 4 brain. So if the information cannot start from this area, and decorticate posturing would occur as a result. For the lower limb, it's similar to decerebrate posturing. It's extension of the ankle and knees. But the difference is here, the arm is flexed. And this can be explained by the involvement of this red nucleus. So red nucleus, because red nucleus is below the forebrain, red nucleus can actually generate the signal to the spinal cord, to the muscle. So it can actually flex the arm in this position. So this posture is commonly seen for the stroke patients where they have the damage to the cerebral hemispheres, internal capsule or thalamus. If you go down to the spinal cord, we can say the role of the spinal cord would be the pathways, the highways. It provides the highways for sensory and motor function. So we covered in week 1 the ascending pathways and motor pathways, descending pathways. And specifically the descending pathways, the vestibulospinal and reticulospinal pathways are considered as medial upper motor neurons. And this is controlling the axial muscles. So by controlling the axial muscles, it's intimately related to postural muscle synergies. In the brainstem area, one of the most important areas in the brainstem controlling the balance would be vestibular nuclei. So it receives multiple information from different sensory systems. So for example, first of all receives the information from vestibular apparatus, so semicircular canal, utricle and saccule sense the head position and balance signal to the vestibular nuclei. And also visual information is fed directly to the vestibular nuclei, and the example was the vection. So by moving the large area of the visual field slowly, we can actually sense the movement. So that's an illusion, but that's done by direct connection between the visual information to the vestibular nuclei. Vestibular nuclei also receives the information from the neck proprioception. So, in other words, it's vestibular system, visual system, and somatosensation system all integrated in the vestibular nuclei. So it can possibly the site for integration in re-weighting signals of the sensory system and relay this signal to the other motor area to organize the proper postural control. The other site important is reticular formation, and people propose that this will be the site for organizing postural synergies. So it might be the higher centers, so involved in central set, to determine which synergies to choose from at different context. So in this diagram, you can see the different inputs and outputs of the vestibular nuclei. So these are the sensory signals received, and these are the output signals from the vestibular nuclei. So if it goes to the cerebrum, it will feel or we will perceive the self-motion. If it go down to the spinal cord, this VSR is vestibulospinal reflex. So it's using the vestibular spinal tract to activate the extensors of the lower limb. If it goes to the cranial nerves, which controls the eye movement, it can create the VOR. VOR stands for the vestibulo ocular reflex. So what it does is it sends the head position signal to cranial nerve number 3, 4 and 6, which are all involved in moving our eyes. So for example, you can hold your lecture note or your laptop and you can actually shake your head left and right. So let's say this is you, and you just shake your head left and right rapidly, and you still be able to read what's in the note even though your head is shaky. And this is done by vestibular ocular reflex. It stabilizes the gaze because what this information gives to the cranial nerves 3, 4 and 6 is how to counteract the head motion. So it's like algorithm that you can find in the digital camera these days to counteract the shaky hands, to focus more on the stable image, produce stable image. So without this reflex, or some patients lost this function, he or she might be view the word as you're holding the camera and just record a video, and you watch that image later on and it feels very shaky. And this is, while watching that video, you might feel dizzy because it's not stabilized. So in other words, they will be very feel very dizzy every time they move their head, and as a result, they might have the stiff neck, because they don't want to move their neck much, because all the time they move their head, it feels dizzy. So stiff neck is common complaints for those who have lost their function, VOR function, gaze stabilization function. So I'm just saying vestibular ocular reflex not working, and as a result you'll have stiff neck. Let's go up the brain. Cerebrum, cerebellum. Sorry. So before we go to the cerebrum, cerebellum is also important site for postural control. This is the diagram showing the different zones of the cerebellar cortex, and also deep nuclei that are associated with those cerebral cortex area. Cerebellar cortex area. So cerebellum can be functionally divided into three parts: lateral, intermediate, and medial. And because it's divided in three different ways due to its function, the deficits are quite unique according to the function. So for example, this medial part, if the patients have stroke in the medial part is also known as vermis. The main deficit would be postural or gait, or unstable trunk for postural control. And if it's caudal area of the vermis, it will also cause the oculomotor problems, or also known as abnormal eye movement. Called nystagmus. For the intermediate zone, this is called paravermis. And the symptoms would be upper limb ataxia or dysarthria. So dysarthria is related to articulation for speech. And upper limb ataxia can be also seen for undershooting or overshooting the target with using the upper limb. Shooting. So the motor deficits related to postural control is mainly at the vermis. And this shows you the blood supply to the cerebellum. So superior cerebellar artery supplying the area here, and posterior inferior cerebellar artery supplies the area down. So vestibular cerebellum is also known as medial zone, involving the vermis. Spinocerebellum is intermediate. Zone and involving the paravermis. Cerebrocerebellum is lateral zone, involving the lateral cerebellar cortex. This cerebrocerebellum area is particularly related to motor planning. And a well-learned, skilled movement. So in the patients who suffers from cerebellar stroke, would show mainly the postural instability or exaggerated correction. So larger than normal corrections. So you would normally see them have wide base of support because of the fear of falling. So when they stand or walk, they will have large base of support. And their gait would be similar to the person who are drunken. So ataxia is also known as drunken gait. So the timing and coordination would be the issue for the motor deficits created by the cerebellar damage. Let's move on to basal ganglia. So cerebellum, basal ganglia, and cerebrum are the three main high motor control centers in the brain. So what's the function of basal ganglia? For posture, basal ganglia is also related to organizing the central set according to the context. So similar to reticular formation, you can form a central set and choose appropriate synergies. Parkinson's disease, damage to the substantia nigra, the part of the basal ganglia, and as a result, dysfunction of basal ganglia can be seen in the postural control. So let's have a look at the difference between young subject and Parkinsonian subjects in controlling the disturbance of posture. So this case shows you the moving of the platform in three different ways. Flat surface, and the perturbation is small, and you would expect this person will show ankle strategy because it's the small perturbation. So this is the schematic diagram representing the same set of the EMG signal. Gastrocnemius first, followed by hamstring and paraspinal postural muscles. Paraspinal muscles, so distal to proximal fascian, dorsal, that's ankle strategy. For when the young subjects are in the narrow, standing on the narrow base of support, and when it moves in larger amplitude, and you can see the hip strategy. So hip strategy is proximal to distal fascian and ventral, so abdominal muscle followed by the quadriceps. So this is the hip strategy. When they sitting on a stool and the stool's moved, not really, the leg muscles are quite silent, and only activation occurs in the paraspinal muscle. What about Parkinsonian subjects? Parkinsonian subjects in a flat surface, small perturbation, and the characteristics of EMG patterns are like this, and you can just simplify in this pattern. What's noticeable is this co-contraction of all the ventral and dorsal muscles at the same time. So this is showing the co-contraction. So you can imagine this patient's being very rigid. Let's change the context. Beam surface, so it's narrow beam and moved larger amplitude, moving larger amplitude. And the pattern is exactly the same as in the small perturbation. So co-contraction again. What about in stool? So the person is sitting on the stool, and again, there's no change in the pattern of muscle activation. So selecting right synergies for different contexts is impaired in the Parkinson's disease patients because the primary role of the basal ganglia is to select appropriate synergies, postural synergies for different contexts. So implication is the Parkinson's disease patients has high risk of falls because of this inflexible postural control strategy that they apply. And lastly, cerebral cortex. It is involving postural control in many complex ways, and especially it can actually influence the postural control in accordance to the cognitive state or psychological state. So, for example, if you have fear, and that might be related, might influence the postural control by the involvement of the cerebral cortex. It can also influence the postural control by prior experience, prior warning signal. So, for example, by looking at the ice on the road, it can actually prepare, your body actually can prepare what sort of postural sets going to be used when you step on the ice later on. So again, it is also involved in organizing the central set, as with the basal ganglia. APA, anticipatory postural adjustment, is known to be involved in supplementary motor cortex, and this can be found in the medial aspect, ventral to the primary motor cortex. The other parts of the cerebral cortex, especially the parietal lobe and temporal cortical areas, are related to spatial orientation, which is crucial in recognizing the relationship between environment and body. And one example was this left area, the left neglect. By the right hemisphere stroke, especially right parietal lobe stroke. And this is the patient who suffers from the right parietal lobe stroke. So this is the template they have to replicate, and they only replicated this using this template, and only the right side is shown, and they're neglecting the left side. So in their world, the left side doesn't exist. Okay, so let's finish at this point.